Right. I'd like to review some of later part of last lecture, some important content. Previously, we suffered from the direct modeling approach. Somehow we escaped from that, but we should know the final result of that suffering. Okay? So let me review this. The section title is Small Signal Dynamics of Parallel Loaded Series Resonant Converter. So the idea is not that difficult here. This is the circuit diagram of parallel loaded series resonant converter, and this is the startup response waveforms. This one is this tank current waveforms, and the lower one is the out voltage waveforms. There are three frequencies involved with these waveforms. First one is this one, omega SO, as the switching frequency of bridge circuit. We call it unmodulated switching frequency. And another one is this resonant frequency of this tank circuit. Okay, tank resonant frequency given by this expression. And the most important frequency is difference between unmodulated switching frequency and resonant frequency, as expressed like this. Okay, because when this omega naught is larger than omega SO, then you don't have to worry about this. But if the omega SO is larger than omega naught, then you need this one. So we are using this sign. It's called envelope frequency or beat frequency. Beat frequency. Your heart is beating like this. There is. So beat frequency. Name of the beat frequency, maybe it came from this fact. If you take a look at the tank current waveforms, there is a high frequency switching waveforms, and the envelope of this is this one. So it's kind of a beat waveforms. It's beating, becomes strong and becomes weak and becomes strong and weak, so on. These dynamics are coming from the tank resonance circuit, and this is the out voltage waveform. So if you take a look at this, it goes like this. Okay, and there is some period. This period is defined this one. So the frequency of this envelope is defined as omega E and B. Okay? And we conclude that this frequency is given by this. Right? If this distance between two frequencies are large, then it comes at high frequency. If it becomes smaller, it comes at lower frequency. So this omega E and B, location of the omega E and B will move around when the switching frequency varies. There is one inherent characteristic of this converter. And so this is the beat period related with omega E and B or beat frequency, and this TSC is just switching frequency, unmodulated switching frequency. Right? And this if you see this dynamics, the out voltage is something, it follows this envelope dynamics. So this is the typical waveform of out voltage. So this beat dynamics here is reflected here. Okay? What we are trying to do is trying to find out some equation or expression, or we want to understand relationship between this variation in switching frequency and this dynamics. Eventually, this will be the output of our converter. So this is we want to know the relationship between this switching frequency variation and through this variation of this envelope. Because this variation is very similar to the variation in the envelope. And so there should be some close relationship between those two frequencies. Okay. So again, our final goal is we want to derive some equation that provide the information between change in the switching frequency to this dynamics, right? So that is our approach here. So this shows the converter dynamics. This is the copy of the previous waveform of our voltage of our converter. So it looks like this. It has some behavior, and this comes from the envelope dynamics, beat frequency dynamics. Right? If there is no this resonant tank sub, like you have some low pass filter like that, then the output will be something similar to this. So this dynamics is coming from the fast tank dynamics. So we call it, we mentioned that this behavior is coming from the fast tank dynamics. So this part is related with this part. And if this is directly connected or replaced with some low pass filter circuit, then the output will be something similar to this. Okay? So this, you are seeing this kind of waveforms in PWM converter usually. Okay? On top of this, we have this beat frequency dynamics coming from this tank circuit dynamics. Right? So frequency of this is related with this omega ENB frequency, and this peaking or this oscillatory behavior is related with quality factor of that double pole frequency, that double pole. All right. So we derive this omega ENB is given by difference between this unmodulated switching frequency and the resonant frequency of resonant tank circuit. And this Q ENB is the Q of this resonant tank circuit. Okay, usually the Q is very high. If Q is much larger than 0.5, this approximation becomes very accurate. So this Q is simply, this is the same as this one. Okay, so and you have this expression. This is the resonant frequency of the tank circuit. So suppose first the switching frequency, unmodulated switching frequency is here. Then we move the unmodulated switching frequency here. Okay? This situation is the same as the changing steady state duty ratio of your PWM converter. If your PWM converter duty ratio is 0.5, output is input times 0.5. You move your duty ratio to 0.2, then output voltage will be reduced, but there is no change in the dynamics because this resonant filter remains the same. So dynamics is coming from only from the low pass filter, nothing will be changed. But situation is different here, okay? Because you move your switching frequency from here to there. It's the same as increasing your duty ratio from, for example, 0.5 to 0.3, 0.5, okay, in the PWM case, okay? But there is a huge, the difference is coming up because this is omega ESO, omega SO, then with this blue line, we call it case number 1, that omega ENB is difference between and this, and the difference is small, relatively small. If you increase this unmodulated switching frequency, then the omega ENB will be this much. Okay? You increase the omega ENB, then the dynamics in the up voltage due to the tank dynamics will be faster, right? And if you increase this one, then that is the same as the increasing this Q ENB, because this omega ENB coming in the numerator of Q ENB. So if you increase the switching frequency, you are increasing both the frequency of the omega ENB and the quality factor of omega ENB. Their result is summarized here. So this can be considered as the output waveform of when your switching frequency is here. When your switching frequency increase, okay, then all of a sudden this frequency becomes higher and the peaking, this oscillatory behavior becomes severe. You understand this? Right? This won't happen in DC-to-DC converter. The dynamics almost remain the same regardless of the value of steady state duty ratio. Okay? So the unmodulated switching frequency in the resonant converter is very similar to the duty ratio of the converter. Okay? Because it's very complicated because we are changing the switching frequency and we are also changing the modulation frequency. Okay? PWM converter, there is a clear distinction between duty ratio is one thing, okay? And switching frequency is another thing. But here we have unmodulated switching frequency and modulation frequency. There's entirely different thing, but the outer shape external shape or term is the same. Okay, both of them are called the frequency, so it's very confusing. But you should have clear distinction between switching frequency and modulation frequency, same as you have clear distinction between Dewey ratio and the switching frequency for the PWM converter case. Okay, that is very important. So next, we just investigate the relationship between the tank dynamics and the envelope dynamics. So first, this is the tank dynamics. This is parallel load series resonant tank circuit. All of these are standard. So there is this relationship. This is the equivalent resistance. Okay, this is the reflected from the output port of the converter. Then this looks like the inverter. The result remains the same. And this is the standard second order coordinate equation and omega naught here. And this is the Q of this resonant tank circuit. So from this Q and omega naught information, we plot this. Okay, this is in omega S plane, and this is the Bode plot of this transfer function. This low pass filter. This peaking is very large, so we are using this part as the band pass filter. Okay, so we are taking advantage of this high Q band pass filter, high Q resonant low pass filter. Then, if you take this part locally, it's very similar to the band pass filter. Okay, so relationship between this tank transfer function and frequency to envelope transfer function is determined here. We derived this. Maybe we spent 2 weeks for this. All right, this is a summary of that result. So this is the switching frequency. This omega SO is unmodulated switching frequency, is modulated by this modulation signal. So this is the variation in the switching frequency, and this is the switch and tank network is here. Okay, then the resonant circuit, resonant tank is providing this kind of waveforms. All right. So suppose your unmodulated switching frequency is somewhere here, and you are changing frequency in between here. Okay. Then the output of this, because at high frequency gain will be small, and at low frequency gain will be large. So you have this kind of waveforms. Okay. So this is envelope, and this is a high frequency tank resonant circuit. So this part is called envelope. Okay, envelope, and you just remove the DC part of this, then you have these waveforms, AC waveforms. Okay, this is called envelope sinusoid, and this is the variation in the switching frequency and transfer function from this to this one. Transfer function from here to there is called frequency to envelope transfer function, and that transfer function is defined as function of modulation frequency, omega m, right? So omega m, okay? Then what is the relationship between this HS, which is the tank transfer function, and the GENB, which is frequency to envelope transfer function? It has very long story, very complex derivation using something, okay? Bessel function analysis and phasor analysis, and conclusion of that result was this. GENBS is related with HS, tank transfer function, in a very complex manner. So it has many terms, okay? So H is transfer function itself, and N is numerator part of this tank transfer function, and D is denominator part of this transfer function. So it's very complicated expression. And particularly denominator is this one. So this is denominator of this tank transfer function, but this frequency is different. S is replaced with S plus J omega SO here. There's one term. Another term is this one. So there are two terms in the denominator. And denominator important. Denominator is important because denominator provide all the information about the poles, and poles determines transient dynamics, and most importantly, stability of the system. Okay, so pole is important. Okay, and numerator is very complex, but fortunately, this numerator has only zeros. Okay, numerator is just providing zeros that occurs at very high frequency, very high frequency. So you can ignore them when you are considering the dynamics within the control bandwidth. So actually, this you forget about this. Assume this is 1. That is fine. Okay. So I wrote down here the numerator of this one. This we call it big numerator. Only provide zeros at very high frequencies, and can be ignored for the dynamic analysis. So only our concern here is denominator of this equation, the GENB equation. This is the final result, our direct modeling approach. Okay. So suppose this is denominator of your tank transfer function. So then from this information, you can locate the 2 poles here. One is here and the other one is here. They are complex conjugate poles. So one here. Okay. Then only difference between this denominator of tank transfer function and the denominator of this envelope transfer function is you only have ds here, and you have these 2 terms. One is s plus j omega or j omega naught, okay, and the other one is s minus j omega naught. That means this one pole. No, you have this, okay. Then this term will be shifted to this place, this upper place, and this term, if you evaluate this, these 2 poles will move to this position. Okay, you can easily prove this. Then result is there are 4 poles or 2 double poles. So one double pole is coming here, another double pole is coming here and here. Okay, they pair like this. They don't pair like this. Okay, because they should be complex conjugate form. But the distance between this point and this from here to this origin is the frequency of this pole. Frequency of this pole is distance between this origin to that pole, but this is much larger. Means this pole is much higher frequency. We ignore this. We just take 2 of them. Okay. Originally we have 2 poles. Also we have 2 poles here. This approximation. Okay. We are ignoring the high frequency dynamics and only taking the dynamics of these 2 dominant poles. Okay. And dominant poles are located here. Then because it is complex conjugate, then you can define this omega ENB and Q ENB. Then we have this expression. This is also second order expression, but we need to evaluate the relationship between this QNB and this Q or Q naught, and relationship between omega ENB and the frequency omega naught. We have done this here. Right? So everything is clear. Right? So this is the simplest possible summary of previous approach. Okay? People call it direct modeling approach because it directly deals with the location of the poles. The other method, phasor transform method, is very similar to this, but it just uses the phasor analysis, and the meaning of that analysis is more abstract than this. Not easy to understand. This one is very easy to understand. Okay? So actually, first they used the phasor transformation method, and later they found out this direct modeling approach. So this one is much easier to understand and much easier to use. To use the phasor transformation method, you need to use some circuit simulator or MATLAB, the mathematical tool. Okay, but here we don't need that. Okay, just we understand this phenomena. If we trust the result of this, then we are okay. Okay. Then hard part is gone. All right. Then next journey is relatively comfortable. I hope so. Okay. This is another summary of tank dynamics, and this slide shows how to extend the result of the previous analysis only concerning with the tank dynamics to dynamics of out voltage, dynamics of resonant converter, not inverter, as shown here. Okay? So this is the concept. So originally, this is the tank voltage waveforms. And after this is modulated like this. This frequency is modulated and amplitude is modulated. Okay. Then you have this rectification. Okay. Then this is the rectified. Or okay, let me say this first. This is a converter. Okay. But if you take a look at this part through this port, then this everything is converted to one single resistor, and that resistor is called RE here, and the value of RE is this one, pi squared divided by 8 times R. Right? We know this, right? Because it's the result of this sinusoidal approximation. So you know this. So you have this voltage waveforms, but you have this resistor. Then through this resistor, it will be changed the current waveforms, and the current waveforms rectified here. This envelope is also rectified. Then with this high frequency part is removed from this branch, and remaining is this one. This should be our voltage of your converter. Okay. So in small signal sense, this is the modulation. In the switching frequency, sinusoidal modulation, and frequency, this one is modulation frequency, and this one is envelope, and this is the same, right? Because you divide by this one RE, it becomes current waveforms, so this remains the same. So there is only scale change in between by this one. This is a resistor, right? And this is low pass filter characteristics, and this will be multiplied to this one. Input impedance of this low pass filter consisting of capacitor and load resistor. Input impedance of that part is denoted as GIF. Okay? So transfer function from the frequency to our voltage is this one. Frequency to output, right? We analyze this switching frequency to envelope transfer function. Next one is, this is envelope to inductor current transfer function. The gain is very simple. There is only one resistor, so 1 over RE is coming here. And finally, this is the input impedance of this part. Okay, then you just multiply the input impedance of this here, right? Then the final result is this one. This is frequency to output transfer function. It has this factor in front, and this part is coming here, and finally it comes here, right? So everything is simple, right? Then evaluate this one. This is the GIF, input impedance seen through this parallel branch of capacitor and the ESR and the resistor. This one, then it is input impedance of this part has 1 0 and 1 pole. This 0 is called ESR 0, and it is generated by the ESR of the capacitor. Omega ESR is coming in the numerator, and the pole is coming in the downstairs. So omega PL as this one. Okay. If R is much larger than RC, which is true for the most cases, you may ignore this, right? Anyway, you have 1 0, 1 pole, this gain, and you multiply all them together, then you have this. This is G, E, and B. It's separated into two parts. This is the DC gain. Okay, evaluated at 0 frequency. We are talking about the modulation frequency. And this is the denominator. We know this. We went through this. There is a big numerator coming here, but can be reduced to 1. Right? So no problem there at all. And you have omega ESR and omega PN. Then final form of transfer function is very simple, which is this one. But we are assuming this is just 1. Right? Because it has only zeros at very high frequencies. Assume this is 1. Right? And this one is just constant. This one is constant. So later on, maybe we evaluate this. This is constant. And it has this omega PL. It comes relatively low frequency, very low frequency. And there is omega ESR generated by the RF capacitor. Series connection of the ESR and the capacitance always generate a zero function. So zero is coming here. And this is what? This is, it comes from this envelope, sinusoid dynamics. You have all the knowledge about this. This is reduced to 1. Then with this, there is a pole assigned in the omega m plane. So here is one pole S1 and S2. They are complex conjugate. They are coming from this part and omega PL across at low frequency here and omega ESR maybe somewhere here. Right? So like this. So distance here is value of the omega ESR. The value of omega ENB is the distance of this one, right? So omega ENB is occurring at higher frequency because the length is larger than the distance between this and this. Okay? Then just take a look at the plot, Bode plot of this. So it has low frequency gain, and this PL, pole is coming first at low frequency. So this zero slope is reduced to this -1 slope, indicating the -20 dB per decade. And you have 1, 0. So this becomes flat here. So we have 0 slope here. Okay, this should be -2, not -1. And you have -3. You have double pole at this omega E and B. Okay, so 0 is reduced to -2. -2 means -40 dB per decade slope. Right? So this is very easy. Right? How about phase? You are not considering the sign of this low frequency gain. Assume that is positive. Then it starts from the 0 degree and go down to 90 degree and some peaking, and it reduced to -180 degree. Okay, but this is always this is portrayed in omega m plane. So forget about omega s now. Everything is omega m as a frequency, different frequency, very different frequency of the switching frequency. Is called the modulation frequency, right? So this is the content of the next lecture, and this is new one. This is an example. One guy generated this plot, all right? So I'd like to show the relationship between our previous analysis and the result of this simulation. This is generated with some method. Actually, it is generated with extended describing function method by one guy. So we are just taking a look at the result of this, right? So this is GVF frequency. Now we change the frequency from omega to F somehow, okay? Because I took several data in different references. Some guy use F, some guy use omega, okay? So this is the frequency gain, and here the omega PL is coming here, and the omega ESR is here, and this is omega E and B. Right? So this is the phase curve and magnetic curve. They are very similar, very in good agreement with our previous analysis. Okay, and this omega E and B is given by this resonant frequency minus unmodulated switching frequency. Because this ratio is lower than unity, it means the switching frequency is located below the resonant frequency, somewhere here. Usually the operational region, operational frequency somewhere here, but somehow he used this in his example. So this is the situation, right? And this is fixed. This omega ESR is fixed. It is always fixed. But this one, omega PL, is not fixed. Later on, we'll see this pole is moving around a lot. Okay. I don't have any good explanation about that, but numerically that is found. That is found. So expression, I cannot use equal sign here because it's moving. If you change the switching frequency, it's moving. This pole is moving a lot. Okay. If this pole is moving, when you change this load resistance, this pole is changing. That's fine. Okay. That is the natural things. But if you change the switching frequency, still this pole is moving. So I don't have any reasonable explanation for this other than this simulation result. Okay. So I don't know why it's moving, but I know it is moving. Okay. Somehow it is moving. And this low frequency gain, G, VF0. Okay. This one is some constant and times G, E, and B evaluate at switching frequency, at this 0. Modulation is gone. So at the modulation frequency, okay, at unmodulated switching frequency, that becomes just taking the derivative of this H curve, okay, is proportional to that, right? That means if this VG and B is larger at this frequency, this DC value, G, E, and B 0 is 0. Because you have this horizontal line here, and the slope here is positive, no negative. For the GBS operation, this gain becomes negative, and only for this GCS operational region, this becomes positive. Okay. I wrote down all the important things. The omega ESR is fixed, so those omega ESR is often omitted. We don't include this for the forthcoming discussions. So that is fixed, already known. Okay. Other frequencies are moving when this unmodulated switching frequency changes. So in that analysis, we just ignore this omega ESR. That is fixed. Okay, so we ignore this. But somehow, in contrast, this will be changed. That is true because it's given by difference between this resonant frequency and this unmodulated switching frequency. When this is changed, this should be changed. But in addition to that, somehow this FPL is also occurs at very different frequencies depending on the value of unmodulated switch frequency, omega S. Okay? For the numerical validation, so this experiment was done. This is taken from the parallel loaded series resonant converter, and the value of the RC and the C are given, and value of all the information are given. So based on that information, I evaluate omega ESR, which is 2 pi RC C. Okay, because 2 pi is necessary. We went to the Hertz region, so value here is 2 pi RC was. I took this information from his dissertation. So this is 45 kilohertz. So omega ESR is somewhere here. 45 kilohertz is a very reasonable number. So 10 kilohertz, 20, 30, 40, 45, something like that. Okay? And switching frequency of this setup. The simulation is resonant frequency was 414 kilohertz. And switching frequency was the ratio between this was as shown here. He specified all these details in his presentation. And Fs. Then Fs is 280 kilohertz. Then omega ENB. No, FENB. The same thing, right? omega E and B. Okay, I use omega E and no, I already use F, right? So F E and B is this one minus this one 134 kilohertz. Okay, so F E and B is somewhere. So 100 kilohertz, 30 something. So this is a very good result. Okay, so we trust this. All right. So this is the main result. Right. So once the switching frequency and resonant frequency is given, you can generate this. But you should understand the behavior of this. What will happen to this GVF transfer function when switching frequency is changed? That is very important. Okay, that information is shown here. Numerical analysis of GVFS. I showed this. I used this to provide the qualitative explanation about the frequency to envelope transfer function. So I'm using the same graph. Actually, this is he generated this for this purpose, but I used this graph, this result for something else. Okay, so I mentioned that was just the conceptual illumination is not exact one. Okay, this is the exact one. This graph, this plot was this one, frequency to output transfer function of parallel load, the series resonant converter. Right. So it is ratio between this switching frequency, unmodulated switching frequency, and the resonant frequency, and this axis represent modulation frequency. Okay. If you select your unmodulated switching frequency at particular value, for example, for this red one, the ratio is 1.2. Then you have one set of curve, which like this, right? If you select the ratio between this omega SO and omega naught, this 0.6, you have this curve, right? So we have seen this curve in this direction in the previous lecture slide, okay? But now you are considering bunch of this graph. If you slice one here, slice another here, then you have this layers of this transfer function arranged in sideway like this. Okay, you understand this, right? And at this particular frequency, okay, take this one as an example. You determine this switching ratio between switching frequency and the resonant frequency is 0.6. Then you take a look at this curve. Then modulation frequency is this one. Then this is the value. So this is the magnitude of that frequency to output transfer function, and phase is somewhere here, right? So if you increase the modulation frequency from 0 to here, there is no modulation, and then this one, the gate will be changed. Okay, so we use this or not. Okay, this provides very good information. I like this graph a lot. Okay, right. So this is the magnitude. So we all know this. This is a phase, right? So if you take a look at the phase, okay, this one. And this is tank transfer function. Okay? It's not related with this one, but somehow I arranged in this manner, so this is very, very good. I think this is a very good approach. But there is some indirect relationship between this, very complicated relationship, right? But this value, slope of this point, slope of this point, slope of this point, is directly related to value of this, low frequency value of this frequency to output transfer function. At this point, slope is 0, so magnitude of this plot is 0. We have this big dip here, this some this dip, big dip. Okay. I cannot remember the word. There is just some special word to describe this. Gorgeous, not gorgeous. All right. Okay. So that is shown here. Okay. This shows the relationship between magnitude of this and the zero value, low frequency magnitude of frequency to output transfer function. So at this point should be 0. Okay. And this slope is increasing. It becomes very large here, something like this, and drops rapidly. It goes like this. Okay. The sign, this part is this region is positive, and above this line, the sign is negative. So if you take a look at the phase was 0, and all of a sudden phase jumped by 180 degrees. So this becomes the sign has been changed. Okay. Actually, it goes negative. It should go down. Okay. Somehow, this direction is okay. There should be a 180 phase jump at this point. Okay. So this explains everything about this. So phase, this magnitude is low frequency magnitude is less than 0 here and is larger than 0. Okay. That is closely related with this curve. Right. This one is interesting. I spent some time to illuminate the dynamics of this converter using this plot. Okay. So if you take a look at this, take just one curve here. So when the switching frequency is only 60% of resonant frequency, it looks like this. It's transfer function. So it has the pole somewhere here and somewhere here, low frequency pole, and maybe ESR 0 is somewhere here, but you are not showing the ESR. You are not considering ESR because the location of the ESR is not moving around. It's absolutely fixed. Then you go down here, there is a double pole. Okay? So there is double pole, right? So it starts from this double pole and this omega PL at low frequencies. If you take a look at this at distance, deleting this red curve and this purple curve, then you will be seeing this pattern. Maybe still you can see this pattern. So when switching frequency is increased from this point to this point, okay, that means you are increasing. You start from the 60% of the resonant frequency and you move around. Okay, you are increasing your switching frequency to 100% of resonant frequency. So you are working like this, and you are looking this curve, this shape, this construction. Then this dipole is moving like this. Okay, it's moving this direction. This frequency is reducing because this is the frequency of omega n. So it occurs at high frequency in omega n, and this frequency is decreasing like this. That consists with our predictions because this omega E and B is distance between this frequency and this frequency and this frequency. As you walk toward this omega E and B will be reduced. So this the peaking should be reduced, and this Q factor is also reduced. Okay. They are proportional each other. This value of the omega E and B and value of the Q is they are proportional. Okay. So this omega E and B is decreasing. Q is decreasing, and at some instant Q is reduced less than 0.5. Then what will happen? That complex pole will be split into two real poles. So one pole is moving this direction, and another pole is moving in this direction. So here, double pole is split into two real poles. Okay, decoupled into two real poles, and one pole is moving into this direction, and this omega PL, it moves from low frequency to higher frequency. As the switching frequency increase, they meet together, then it becomes double pole, and double pole is still moving somewhere here. Okay? So this is the interpretation from the result of this simulation, numerical result. And we are incorporating the knowledge about the dynamics of inverter. Okay? Parallel load series resonant inverter. So we understand this from our previous knowledge, right? So let me show this. We start from here. So there is a double port at high frequency. One here, another one here. Okay? If you move around this, we increase your switching frequency. This Q is reducing, so Q is reducing. Okay? If Q becomes smaller, they come together. Okay? If omega E and B reduced, they come to this direction. It's a combination of the two movement. So final result is moving toward this, moving toward this. Okay? And at this point, this green circle, two poles are split. Double poles are split into two dual poles, and one pole is moving into this direction. One pole is moving moving toward the higher frequency like this, and another pole is moving toward the lower frequency, and this frequency was increasing. They meet together at this point, at this triangular point, and they merge together to become a double pole at low frequency. This one. Okay? So it started out from this one. They are together, they are double poles, and here, okay, and they merged together, and they went here, okay, and one pole is moved here. Okay? So this cross head was the starting point. This can be considered as the final point. One here, and this double pole. That makes sense. We start from the 3 poles, and we arrived at 3 poles. Okay? So that is the general description of this figure. And I have another graphical portrait of this thing, interpretation of this. Okay? Originally, we start out here. Omega E and B at very high frequency. Omega E and B start here. Okay? So they moved. As the switching frequency increased, they moved in this direction because omega E and B is expressed like this, and this is very small, and you are increasing this, then this becomes small, right? So it's decreasing. If you increase the omega SO, then this Q E and B and omega E and B, they both decrease simultaneously. So it moves this point, and eventually they'll hit this point when this Q becomes 0.5. There is the boundary between double pole and two dual poles. This is Q. Here is Q E and B as 0.5. Okay. Then decoupling has been occurred. So decoupling, the omega E and B was double pole, and they decoupled into two dual poles. One is here, another one is here. If you increase the switching frequency further, while during that time, this omega PL was increasing toward the high frequency. If you increase your switching frequency further, they move together here. Then this Q omega L. Omega L is double pole at low frequency. Right, omega L. Then QL is 0.5. Then two dual poles is coupled into one complex poles, double pole. Right? So this is reasonable, right? This is reasonable. I found that this prediction is very accurate. So we combined our knowledge about the tank dynamics and the low frequency dynamics, and somehow we combined our knowledge of that with this graphical analysis, and by interpreting this three-dimensional curve properly, we conclude this behavior of this pole trajectory, right? So this one is not a root locus. Root locus is something different. When you are talking about root locus, you are talking about 1 plus some transfer function equals 0. Okay? So you are plotting the trajectory of root of the equation. This one is something else. Okay? This one, but somehow the trajectory, pole trajectory, is follow the common behavior of root locus. In root locus, two poles meet at this real axis. They split or they merge. Okay? So this is the reasonable understanding of this. Okay? This one is very informative. So we allowed here. We allowed here. Then we have this gorge, the cliff, okay, deep here. So we jumped to here, okay. You jumped here. Then now you further increasing the switch frequency. Then let's take a look at what will happen after that, okay. It is reasonable. The behavior of this region is kind of the mirror image or complementary manner to the previous behavior, right? Because this should be the somehow symmetrical. This part and this part. Because this is symmetrical. This tank transfer function is symmetrical. Then this should be symmetrical. Okay? That should be expecting they will be symmetrical as reasonable. That really happens here. Okay? This is the pole trajectory of GBF when you increase your switching frequency above the resonant frequency. Starting point here is here. You arrive at the top somewhere here, okay, and you have one pole at very high frequency, and you are increasing the switching frequency. All right. So you start out here. So you have double pole at low frequency somewhere here, and you increase switching frequency. Then somehow the Q will be reduced, and at this point it's split. Okay. So it is here. It was hanging around some time, and it split this, and this pole is reducing in opposite. They merge together here, and they split. One goes this direction, at this direction, and another one goes the opposite direction. And this omega h is decreasing in frequency, so it decrease, and they meet together. They coupled as one complex pole, and this complex pole is increasing in switching frequency, in frequency and Q factor, right? So it goes out, and it goes out to this direction because this direction is proportional to the Q, and this direction is proportional to omega E and B. Okay, so take a look at this. Okay, we start out here, and it's split. Then this decreasing, they merge together at this point and go one double pole. And after this, you increase the switching frequency. Then omega E and B will be increased. The omega E and B will be increased, and you are also increasing Q. So it becomes more picky. Okay, there's more pickier. It becomes pickier and goes like this. Okay, so let me mark this again. This frequency. Okay, this one, I can use as many as colors I want, but you are not. Okay, sorry for that. So this frequency, this is split. Okay, this double pole at omega L at low frequency is split into two real poles, and they meet here. So here we have this coupling. Okay, so this is the decoupling of low frequency double pole point, and this is coupling of this high frequency real poles, and they merge together and becomes this omega E and B, and it goes higher frequency and it becomes more picky or pickier. Okay, let me, so it start out this X point. So poles are, so you have 3 poles, okay, one, another one, but they are double poles, okay. Then they arrive to this squared point, okay. There are 2 poles, but it's just one double poles, and one is came in here, okay. This is it okay with you? Huh? Okay. Otherwise, you take a look at this, then it can be understood. Right? There are many alternative interpretation of this curve. So eventually, you will understand everything. So this is the detailed description of that. Okay. So it started out this omega L, and low frequencies. So let me mark X. No. Oh, yes. Oh, this is bad. Usually starting point was X, right? Okay, this might be okay. Then we started out here, okay? And these 2 poles, these dipoles, is somehow they Q is reduced, so maybe the frequency remained the same, right? Because this is almost circular. Then it stayed here, but Q is removed. When Q reduced the 0.5, they split into 2 real poles. One pole goes this direction, and another pole goes this direction, right? So that is shown here. One goes this lower frequency, and another pole goes at this higher frequency. And this omega H was here, and is coming down. It is coming down at omega n frequency, and they meet together here at this point. The omega E and B is at this frequency. Q E and B is 0.5, and Q L is 0.5. So you have this was original double pole somewhere here, okay. Then you have another double pole, new double pole at this point. So now after this, this omega SO is increased. Switching frequency further increased. Then this Q E and B and omega E and B will be both increased. Then you have larger peaking at higher frequency, okay. And it both matches with this prediction, and omega PL goes, this pole goes at low frequency, omega PL here. Okay, so this should be end frequency. So I should use square, Square, right? That's right. Okay? It's very good if you adapt this. If you trust this, that is very good for you. Okay? So it's kind of the combination of the tank dynamics, low pass filter dynamics, and the result of the graphical analysis, 3-dimensional plot, and there is the story. I conclude based on those background. Okay? Okay, so let me explain this. This represents the HT, this is tank transfer function. H, okay, tank transfer function, okay. If you take a look at this curve, around this area, at this center point, you have this zero value. It has the singular point. point showing some strange behavior. And around this, you have double pole at low frequency double pole here. And you have high frequency double pole in this region, this one and this one. And in between, you have two dual poles. Somewhere you have two dual poles. And this region, you have high frequency double pole. And at this vicinity of this clip, you have this low frequency double pole. So that is shown separately in this curve. Okay, the V region is this is the V region. V region. Okay, this is the shape of this H curve. Okay, at this point, if the switching frequency is at the resonant frequency, that becomes 0. Okay, it becomes 0. Magnitude becomes 0. And if the switching frequency is near this resonant frequency, you have double pole at low frequency. If you increase the distance between your switching frequency in either direction, this direction or this direction, you have 3 dual poles. Here you have one low frequency double pole and one high frequency single pole, dual pole. You have 3 poles here. And in here you have 3 dual poles, omega L1, omega L2, omega H. Okay. I'll explain what they are. Okay. So at this region, at the center region, you have this low frequency double pole, omega L and omega L star, and the high frequency dual pole, omega H. Okay. So this region, this one, or this one, you have 3 poles, and we named it as omega L1, omega L2, and omega H, high frequency pole. Well, if you further increase your switching frequency from this tank resonant frequency in this direction or in this direction, then you have double pole and one single dual poles. One is omega E and B. Another double pole is omega E and B. One of double pole is omega E and B, and another pair, another double pole has 2 poles. Okay, one is omega E and B, the other is omega E and B star, and we have one dual pole at low frequencies. That is the conclusion of our previous interpretation. And this one shows the slope of H curve. So at this point, at this singular point, this slope becomes 0. Here, value is high and positive, and value is high and negative. So we went through this previously, right? So by combining all of these, I have another plot. This plot is very good. Okay? Just take a look at this. This is H curve, is transfer function, transfer gain of tank resonance circuit. This is the center. This is resonant frequency. So your switching frequency is at this point, you have this gorge. Okay? You have very big dip. And you increase your switching frequency slightly higher than this tank resonant frequency. You are in this A area. So in this area is this one. So increase your switching frequency a little bit. Then is this A area. Okay? So this area generate this one low frequency double pole at this low frequency, and one single pole, single dual pole at high frequency. Okay? So increase, okay, you increase switching frequency, then this double pole, low frequency double pole, split into 2 dual poles. One goes higher frequency, another one goes lower frequency. So you move this direction, so you are somewhere here. Okay? Then this generate, and this corresponds to this B area. Assume you start here, and you are learning this direction. Looking this one, and you are seeing this, the pole trajectory of frequency to output transfer function. Okay? So you learned here and you learn more. So you go down further than this part. Okay? Then this split dual pole moves to low frequency here, and these two poles they are merging together, coupled into one double pole. And if you run down through this slope, or you run this direction, then this the omega E and B is increasing. This frequency is increasing, and the Q E and B is increasing. So it becomes more peaky, becomes peakier. Understand it? Right? Okay. So the relation between this and this pole trajectory is shown here. Okay. And this, when you stay here, so one pole is here, and this pair of double pole is here, and at this point they merge they split into two dual poles. You are here, then your pole is B, here, three dual poles, 1, 2, 3 dual poles, and you go down further, okay? Then this pole, they merge into one complex conjugate pole, double pole, so it goes like this, goes like this, goes like this. Right? Okay. So this squared one, omega L here. Omega E and B represent double pole. Okay? So with poles inside of this box, green or purple both represent double pole. Okay, let me just show one more page. You can understand this immediately, right? So this is another view of this. You are here. So your pole is somewhere here, and you move down to here. Then your pole is this, three real poles, and you move down further. You have this one double pole and one low frequency dual pole, one here, two here. Okay? So this one is very easy to understand. Okay, very informative. This is not 100% science or engineering, but maybe this is a very good way of understanding this behavior. Okay? You will be seeing many simulation results later. Okay? And I have seen so many cases. They all falls one of this category. Okay? Maybe one point is somewhere here, somewhere here, somewhere here. All right? So using this is very important. Okay? Then with this, you can identify the worst case dynamics when your switching frequency is varied in sub-frequency range. Okay? Suppose your switching frequency is in your previous test, maybe switching frequency is somewhere is limited here, then you have only 3 dual poles. Okay? If the switching frequency range covers here, some region you have 3 dual poles, and the other region you have one double pole and only one dual poles. The dynamics will be there differently. Okay? So you should select which point you design your compensation. All right? And which is the worst case. If you design your compensation for the worst case, that case should be all the desired characteristic for the entire operational region in terms of stability and some other performance. Okay? That is the approach will be taken. Okay? So next week, we start from here and we go into the control design of this converter. Okay? In the similar manner as the PWM converter case, because once this background is set up, then we will use your previous knowledge about the PWM converter case. Okay? Okay, we stop here. Thank you.